นุษย์เราเริ่มตั้งคำถามเกี่ยวกับกลไกการทำงานพื้นฐานของธรรมชาติมาตั้งแต่ครั้งโบราณกาลองค์ความรู้ที่ได้ถูกส่งต่อจากรุ่นสู่รุ่นถูกพัฒนาปรับเปลี่ยนต่อยอดผ่านการค้นคว้าทดลองตั้งสมมติฐานและพิสูจน์ทางทฤษฎีเพื่อให้เข้าใจถูกต้องมากขึ้นฟิสิกส์ทฤษฎีถือเป็นวิทยาศาสตร์พื้นฐานที่สำคัญอันหนึ่งที่อาศัยแบบจำลองทางคณิตศาสตร์ในการไขความลับความเป็นไปของสิ่งที่อยู่รอบตัวเราตั้งแต่ระดับอะตอมไปจนถึงระดับจักรวาลส่วนหนึ่งของผลสำฤทธิ์ที่มนุษย์ทำความเข้าใจธรรมชาติผ่านภาษาทางคณิตศาสตร์คือเทคโนโลยีอันหลากหลายที่อำนวยความสะดวกในชีวิตประจำวันไม่ว่าจะเป็นโทรศัพท์มือถือคอมพิวเตอร์หรือแม้แต่โครงข่ายอินเทอร์เน็ตที่ทำให้โลกอันกว้างใหญ่แคบลงไปเพียงปลายนิ้วสัมผัสยังมีคำถามอีกมากมายที่เรายังตอบไม่ได้ทั้งหมดเกี่ยวกับธรรมชาติซึ่งถือว่าเป็นเรื่องที่ท้าทายและรอคอยให้นักวิทยาศาสตร์เข้าไปค้นหาคำตอบในอนาคตในปัจจุบันบุคลากรของวิทยาลัยเพื่อการค้นคว้าระดับรากฐานถือได้ว่าเป็นส่วนหนึ่งในการค้นหาคำตอบของคำถามข้างต้นผ่านการทำงานวิจัยหลากหลายที่ให้หัวข้อที่ล้ำหน้า
Okay, good afternoon, everyone, and welcome to ETH Colloquium Online Seminar Series number 12, organized by Institute for Fundamental Study, NARIT University, Thailand. My name is Siklin Yukong. I am ETH Deputy Director of Strategy, and it is a pleasure to welcome everyone to this afternoon event. Let me first give you the idea why do we need to do this kind of activity. Most of the time, academic conversation would normally circulate among the scientists, yet it bridging the gap between the science world and general audiences is very crucial for the country in this current competitive world. Then the Institute for Fundamental Study would like to provide a platform for people who are interested in physics, mathematics, and other related fields come and enjoy in progress or the advanced research. For this talk, we have Apimook, Watcharangkool from National Astronomical Research Institute of Thailand, or in short NARIT, to talk on the topic Imprint of Gravitational Wave in Atomic Spectra. Let me spend a bit more time to introduce our speaker formally. Apimook completed his bachelor degree in physics from Chiangmai University, Thailand. Then he went for his master degree in quantum field and fundamental forces at Imperial College London, United Kingdom. After that, he went further for his Ph.D. in physics at King College London, United Kingdom. Currently, he holds a coordinator position of the Cosmology and High Energy Astrophysics research team at NARIT. His research interest is non-commutative geometry and its application in high energy and quantum physics. He also working on high energy astrophysics, cosmology, and black hole physics as well. The talk will be roughly 14 minutes long. Before I stop during the talk, if you have questions, you can put them in the comment. Our staff will collect all the questions and deliver to the speaker at the end. Anyway, without further ado, let me give the screen over to our speaker, Apimook. Screen is yours.
Thank you. Okay. Thank you, P.C. Karin, for introducing me. Okay. Right. So the topic of today will be the imprint of gravitational wave in atomic spectra. To be more specific, I will talk about hydrogen atoms. This is the work I've been working on recently, and this haven't been published yet, but it will be soon. So first I'll talk about gravitational wave in general, and then we describe the behavior of electron in curved space-time using Dirac equation. Then we consider classical limits of this equation to see to obtain the Hamiltonian the Schrödinger-like equation. So we can solve for energy, and then we will talk about selection rule, energy shift, and the way to detect this imprint. Okay. So as you know, gravitational wave has been discovered for quite a while, but it's still a new channel for astrophysics, and we need to understand it better, because it gives us new information about universe, and it has a potential to probe beyond what we already knew. Okay. So the gravitational wave, we think of it as the perturbation of the space-time. If you have a flat metric, you could have the h as the perturbation, and then if you put this back in Einstein equation, what you get is the wave equation. I mean, in a certain gauge condition, you get a nice wave equation like this one. And the solution of this wave equation is the following, right? With the with the two polarization. One is the plus polarization, and another one is the cross polarization. So to make it more friendly, let's look at the picture. You see on the left side is the plus polarization. So you see it's moving vertical and horizontal, and for the cross polarization, it's moving in the diagonal direction. Okay, and the space-time around the point where the gravitational wave pass will move move up and down. I mean, move around as it's propagating, right? And so this thing will the gravitational wave will affect everything around it, as long as the thing lives on the space-time, and it's also affect the electron on the space-time. And we know that electron is described by Dirac equation. So I suppose everyone familiar with the Dirac matrices. It's the matrices that look like this. It's the thing that satisfy the this relation here. The anti-commutator of this element will be equal to the metric, right? This thing, this element is the basis of what we call Clifford algebra. And this Clifford algebra contains what is known as the spin group, and that's why it's related to the electron, because electron is something that is invariant under the spin transformation. And because we are living in the curved space-time, you need a transformation that transform from the flat space, which I put the index, I put the Roman index, gamma A, and the space-time index, I use the Greek index. So this gamma bar here is the Dirac matrices in the curved space-time, and it satisfies this relation below, similar to the one we talked about earlier. Now this is the picture of Paul Dirac, the inventor of the Dirac equation. And the equation 1 is what we call Dirac equation on the curved space-time. You see a technical detail here that it tells you that how the curved space-time go into the equation. You see the omega is the spin connection coefficient, which allows you to define a covariant derivative, which is called the spin connection. It's a kind of covariant derivative, but it's acting on spin. Okay. And the equation 1 can be rewritten in the form of Schrödinger equation, as we put in equation 2, and the Hamiltonian of the Schrödinger-like equation will be as in equation 3. Okay. You will see that for gravitational wave background, you have a correction term, the blue one and the green one. And you have the usual Dirac Hamiltonian, which I write H.D. flat. So because in Dirac equation you have the equation that describe both particle and antiparticles, namely electron and positron. But in classical situation, like in atoms, you only care about electron. So to get the classical limits, we use a method called 40 Woodthausen, which is the method that can put your Hamiltonian in a block diagonal representation. So if you look at the purple Hamiltonian here, the HFW will be decomposed into H plus and H minus. Each one is correspond to electron and positron. So, okay, and in the less understandable way, but it's more practical to the calculation. You will if you look at the last line, you see that the 40,000 Hamiltonian is approximately of this form. It's the combination of operator E, which defined above, and operator O. Okay, we keep this expansion up to fine structure term. So if it's smaller than that, it will be quite difficult to observe experimentally. So we keep it's up to this term. Okay. So this O operator for gravitational wave looks like this. So it's the combination of O0, O plus, and O cross, as you see here. And if we assume that for H cross is 0, so we can ignore the O cross term. Just for simplicity, because we can decide what polarization we are interested in, and we want to consider the case where the vector potential is 0, because we interested in hydrogen atoms, which you only have the Coulomb potential, right? And in such a case, your plus and minus Hamiltonian, this one in the block matrix form will look like this. So as you as the energy decrease, you will get the energy of H plus, but the H minus term is approaching 0, because that is the energy for positron, which you don't see in your daily life. So from now, we will be interested in H plus of the gravitational wave. Okay. Then so if you look at the Hamiltonian, you see many terms, which some term is of higher order, like the order of fine structure. So we want to consider the case where the electromagnetic interaction is I mean the coupling between the electromagnetic interaction and gravitational wave is stronger than the fine structure term. So we ignore the HFS, which is the fine structure term, and we consider H bar, which is the usual Hamiltonian of hydrogen atom that you already know, and we have the correction term, which is the has the order of H plus, the gravitational wave amplitude. But before we move to the next slide, we shall look at Coulomb potential here, because the separation of electron and proton is the propelling. So we have to consider the effect of a gravitational wave, which vary the strength, this distance between between proton and electron, and your potential will have the form like this. It's depends on the first order of gravitational wave amplitude. Okay. And now, since we say that we would like to study the case where the Hamiltonian of the gravitational wave is much larger than the fine structure term, but still can be considered as the perturbation of the hydrogen atom Hamiltonian. And then by assuming this, we can use the perturbation theory to find the energy of electron in atoms. So when you when you compute first order perturbation, you use the basis of the hydrogen atom, right? The NL and M basis, and you compute this correction. So to make it easier, we use what's so called Wigner-Agate theorem and represent the Hamiltonian here as a tensor, the second rank tensor. And the result of this theorem tells us that we get the selection rule that the metric elements you see here will be 0 unless delta L and delta L, unless the delta L is either 0 or plus minus 2, and delta M is plus minus 2. So in usual quantum mechanics, you have the selection rule, which is delta L equal 0 and plus minus 1, and M is plus minus 1 as well. That is correspond to the dipole transition, which is the the dipole is so it corresponded to one photon transition between the two states. But when you have selection rule plus minus 2, this is the quadrupole transition, which is usually very, very difficult to occur, and it's correspond to two photon transition, not just one photon. Okay, so you have one photon coming and the electron jump to a virtual state, and then another photon coming to get to this excited state. So you need 2 photons. So the meaning of this is that you has you have a process that require spin 2 interaction to get you up to the excited state, which is the evidence that we the evidence that there is something to do with spin 2 particle or something like that. And we can compute the the energy shift of the atom by put together the energy of hydrogen atom and add in the correction term, which yield the following energy split. So the 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 level 2 no, sorry the level 200, which is I label here epsilon 1, and the level 210 would be it would have the energy E2, so it doesn't affected by the propagation the perturbation of gravitational wave. But the next level, you see that there is a splitting from the E2 by the order of H. Okay, so you have the coefficient 4/5 H plus, and we think in an appropriate environment this energy shift can possibly be detected. Okay, so if we think about a gravitational wave source like a supermassive black hole, so the strength of the gravitational wave will be given by this formula here, which for our regime where we want the perturbation of gravitational wave to be bigger than the fine structure term, you need the h to be around 10 to the minus 2 or to 10 to the minus 4, which corresponded to m around 10 to the 10. That would be a supermassive black hole, and the place where the gravitational wave source is strong enough is around 1 to 100 light year away from the source. So if you have this kind of source, the the hydrogen atom surrounding the source should produce this energy shift. I mean, this is just the n equal to level. The other level also split as well, and that can possibly be detected in well, if it's n equal 2, n equal 3, it's still in the range of visible light. You can use the optical telescope to see it. I mean the sensitive enough optical telescope. Right. So seems to speak too fast. In summary, what we have done is that we obtain the selection rule that caused by the gravitational wave perturbation. So you have delta L equal 0 or plus minus 2, and delta M is plus minus 2, which related to spin of graviton. And the energy shift is of order h, which possibly can be detected. Consider the big, I mean, strong enough gravitational wave strength, which shouldn't be too far away from the source, and the source has to be supermassive black hole binary. Okay. And yeah, this is the Pikachu under the gravitational wave polarization. Okay, I think that would be all. I seems to speak too fast. Hello, Ajahn Lin, where are you? Is there any question?
Okay.
Okay. Sorry, I speak too fast.
Oh, sorry for technical issue
Right.
about internet connection.
Mhm.
Well, okay. Well, not too that fast, I think. But anyway, this is very interesting topic. I could not imagine that actually the gravitational wave will affect somehow the energy spectrum of
Mm.
this kind of you look at the hydrogen atom, right?
Mhm.
Yeah, very interesting. But anyway, so at the beginning you mentioned actually this gravitational wave would allow us to somehow to probe the universe in different way,
Mhm.
right?
Yeah.
Normally we have to look at it, but not directly look at it by our eyes, right? But
Right.
we need a telescope somehow.
Yeah.
But this discovery of the gravitational wave, we could somehow um, some people say that actually we can listen to the universe somehow.
Yeah.
Is that
So this
yeah?
is the other way. So
Yeah.
you look at the source around the gravitational wave and
Hmm.
see the light it emits to understand uh, the the some other behavior of gravitational wave. Like I mentioned that we can get the hint of the spin of gravitational wave,
Hmm. Mhm,
Like
mhm.
it's it's still a question that can we actually call this a spin, because you don't have quantum gravity, and how this thing calls spin, we can call this thing spin. But I would say, if it's spin is not something that is quantum. Spin is something that's you have as a representation of some particular group. If you have the group, you have certain representation, then you can call that spin. And
So what? Okay. 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 Let continue. Okay.
yeah, and as you see that we use the this correction is the tensor, right? And you did uh, consider the representation of this tensor on some finite dimensional Hilbert space, then you automatically get the spin.
Mm.
Mm.
So, in your opinion, is that the spin is not somehow physical property, but rather than to
It,
be
I mean, it is,
uh,
but it depends on how you describe it. Um, well, spin is mathematical thing. It's something that related to the group, but you say that it's physical property because you can measure it, and now you
yes.
have a way to measure this quantity. Then well, it's physical as well as mathematical.
Mm, mm. Yes, that is very interesting point because you mentioned that actually this spin can be described by some mathematical property about symmetry of the
Mhm.
group, that kind of thing.
Mm.
And yeah, I don't have, I don't know actually the answer for this, but well, anyway, that is a very interesting point. Anyway, so and then you look at the Dirac equation on the curved space-time because you are interested in the effect of the gravitational wave on somehow on
Mm.
the electron, right?
Yeah,
Or more specifically on the fermion. Is that right?
yeah.
Yeah. So my question then, what about boson? Is it? Can you do this?
Well, boson boson also affected by gravitational wave, but I don't know. Uh, there are many experiments that consider the effect of gravitational wave on boson. For example, the atomic interferometer, that you have the atom in certain state,
Mm-hmm,
and you put it under the influence of gravitational wave, and
mm-hmm,
see how these atoms interfere to each other, because atom has a phase, right?
mm-hmm,
The phase of quantum particle.
mm-hmm,
And then when it go past the gravitational wave or gravitational potential, your phase can be different, and then after it pass different path, it can interfere to each other.
you can see the interference pattern somehow
Yeah,
shifted or something like that, right? That is very interesting.
so
Okay.
we don't we can't really look at atom as the particle or a clump of particle. It's it's something, it's quantum. So it's the excitation of something, and when it's interfere with another quantum system, it can show you different excitation.
Mm-hmm, mm-hmm. Okay. Okay. All right. Okay. And then okay. So and then after that you went through so like uh, a very complicated. Well, I don't want to put this word, but yeah, mathematics about solving the Dirac equation, and then you look at you ignore some terms of it, and then you treat your system as a perturbation, right?
Mhm.
And then yeah, and you get what you want, and then I believe that so what you get at very end, so you look at the selection rule, right?
Yeah.
And you find out that actually the selection rule change under the presence of the gravitational wave, right?
Yes.
Yeah,
Yes.
that's what you get. And I'm not really sure that what you put in this in the slide actually two photon transition that is
Mhm.
as it's the new your new selection rule, right? That kind of thing.
Well, the two photon two photon transition is something already exists in
Yeah.
the literature, and is something that we already been detected for
Mm-hmm.
long time,
Mm-hmm.
but it's pretty rare
Mm-hmm.
in electromagnetic channel. Usually
Mm-hmm.
you will get the dipole transition
Mm-hmm.
because you have when you do the say when you have the Coulomb potential,
Mm-hmm.
or you have the potential, you can do the multiple expansion, right? And
Mm-hmm.
the term that is significant is the dipole term.
Mm-hmm.
And this dipole is what you use in quantum to
Mm-hmm.
interpret the transition between the energy level of electron. But the higher order term also
Okay.
uh,
All right. Mm-hmm.
also possible, but the strength is weaker.
Mm-hmm.
Mm. but but it exists, and
Okay.
uh, for when you have gravitational wave coming in,
Mm-hmm.
this gravitational wave kind of induce the term
Ah,
similar to the quadrupole transition.
okay.
Mm. And to achieve this transition, you need two photon because it's something related to spin two.
Okay. Okay. Spin two.
Mm.
Okay.
Well, in quadrupole transition, the quadrupole is the tensor, right? It's the second rank tensor,
Mm-hmm.
so
Mm-hmm.
it's not difficult to see that you need uh, spin two to
Mm-hmm.
activate this transition.
Right. Okay. 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 All right. So and also you also your result can also show that there is also energy shift as well, right?
Hmm. Yeah.
Okay.
So
So this
the
can
energy shift part is not new. It's been studied for quite a while, and uh,
we
there
mean
are
from the gravitational wave.
yeah, there are people that study the energy shift from uh, gravitation, from curved
Ah,
space, and
okay.
there's some people doing um, gravitational wave as well, but the spin thing is new.
Okay. You mean that this selection rule is news, right?
Yeah, yeah. No one
Okay.
has been looking at this thing before.
All right. Very interesting. And so and then there is nothing like the splitting of the spectrum happened here, right?
Oh,
Uh,
there is the
oh,
splitting of spectrum as well. I'm saying that other people has been consider this thing
ah,
before us.
all right. Okay. Then you
So
don't you don't you
they
don't need.
have splitting as well, but
Okay.
maybe they consider the different regime. They
Ah.
they they consider the case where they're interesting in high high frequency gravitational wave, while we interested in low frequency gravitational wave, because
Mhm.
this is what now LIGO detect what's it, it's kind of intermediate frequency, and we need something lower than what LIGO has found.
Okay. And so here I come to the very interesting point, because you
Mhm.
mentioned that actually if we want to detect this kind of phenomena or of effect
Mhm.
of the gravitational wave on the hydrogen atom,
Mhm.
then you need to do the experiment very close to the source of the gravitational wave. Is that
Mhm.
right? So it
Well,
means
I don't need to do experiment there, but
okay.
we can detect the light that come from
Ah,
that area, right?
so
Normally, if you wait for the gravitational wave to come to arrive at Earth, the strength of gravitational wave will be decreasing,
mhm, mhm,
right?
mhm.
But but for photon, it's a bit we it's a bit more detectable. We
All right.
have better technology to detect photon, so
Okay.
it doesn't matter that much. It does matter, but that the photon is traveling far away, we can still detect it, right?
Mm, mm, mm.
Hmm.
Okay, so it means that so we can put the detector on Earth, right,
Yeah,
and look at the photon that
yeah.
coming out
So
around
it's
that
even
source of
better if
gravitational
you
wave.
have, yeah, it's even better if you have the space telescope. But uh, in principle, if the photon from that area arrive, we can see something.
Mm, mm, mm. All right, very interesting. I don't know whether there is a question from the online audience. Um, oh, that is a survey form. It's not a question. Okay,
Is there anyone listening?
you're a student here.
There's one. This guy,
Interesting.
this guy is a nama.
No.
Unicorn is nama.
Okay. Okay. Is there any
He worked with me.
um
He worked with you. You know, he knows both. He's a nama.
Inama? Yes, indeed.
Mm.
Okay. I don't know. Is there any other question or anything online? I don't see yet. Let me have a look. No. Well, there is a Japanese language put in here in the
Oh,
comment. I can.
Dodemo.
Can you read?
Dodemo what? Did it? Cool.
Is mean thank you very much. Is that right?
Non. Dodemo.
What?
Dodemo. It's very something. Kude
Okay.
shi desu. อะไรวะ
Kideska. Is that right? I don't know. I don't know Japanese language. Then anyway.
I I can only read hiragana. I cannot. I don't know some kanji, but
All right. Oh, so this is the kanji one, right?
yeah, there's kanji one.
Actually, I don't know any Japanese
Mm.
kanji or hiragana. Okay. All right. Okay. Also, there is another comment from Suwat in.
Yeah, he is
Um.
my research assistant. So
All right.
this is
Okay.
another nama.
Another nama. Okay. Very interesting talk. Okay. Indeed, it's very interesting.
Mm.
I mean, topic here, because as I mentioned, I this is very, I don't know, I never imagined actually this kind of gravitational wave would affect somehow the
Mm.
energy spectrum of the hydrogen atom.
Well, this is the
Yeah.
idea of my PhD student, and at first I didn't think it possible,
All
but
right.
we like, okay, let's work it out. If
All
it's
right.
okay, then it's okay, and
Okay.
it's become more interesting as we working on it.
All right. Okay.
We find the way to like solve the problem and try to see what like try to interpret
Mm-hmm.
the result that coming out of it.
Mm-hmm. Mm-hmm. Mm-hmm.
Well, we didn't know at first that it will lead up to this point.
Yeah, that is the way it is for research, right? We don't
Mm,
know what at the end what we're going to get, right?
yeah.
That is the fascinating point of the doing research anyway.
Mm.
And but you mentioned that actually this work haven't published yet,
No,
right?
not yet.
You
Uh,
fighting with
I've
April
been
or something,
fighting with
right?
referee. People don't seems to think, don't seems to believe that we can actually see the effect of spin in spin of gravitational wave in this kind of events. But I think I
So
have a
so
friend.
that point is about detecting
Um,
detect this. Is that
they 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 give me some comment which is totally wrong. I've been protesting with the the journal.
okay? Okay, okay. Okay, that is a bit too technical to talk here, I
Mm,
think. Anyway, so I hope that your this work will be get yeah published soon. Okay,
yeah,
and
I hope so.
so
So my PhD student will be graduate.
that is a point,
Be
right?
graduate. I think
Okay,
it's
that's
a
the
very
point.
important point.
Okay, okay. So we can you advertise yourself a little bit about your research? I mean, what you are working on now, or I believe that this is not only
Mm.
the topic that you're working on, right? There is
No,
some other thing.
I
Can you
also
tell
work
people about that?
right. So mainly I'm working on black hole and really related stuff. This is one of them.
Mhm.
Gravitational wave is one of them. Another work I'm working with. Oh, sorry. I'm work with Dr. Perm Wai from SUT. The
Ah,
topic
right.
is the X-ray emission from the black hole corona. So
Okay.
when you have a black hole, um, the active galactic nuclei, you can see that uh, you can see the X-ray from it. So
Okay.
people suspect that there must be some hot electron around it,
Mhm.
which allow it to produce X-ray, right? And I study the mechanism and the geometry of the corona that produce such signal, which I use the technique that is involve Riemannian geometrical optics. So you think of optical medium as a you use GR in optical medium, so the light can you know bend and curve around the source. And another one is the super radiance. So we study the equation that produce super radiance and try to understand it more, and also want to use this phenomena to explain X-ray around the AGN. And the other one, the last one, is still the non-commutative geometry. That I'm been working on with my colleague in Chiangmai University. I was trying to look at the subspectral triple, which mean like you have manifold, you have submanifold, right? So if you have non-commutative geometry, is there a sub? What is the notion of sub non-commutative geometry? Something like that. And it's very difficult. It's very, very difficult thing to
Yeah,
do.
definitely it sounds difficult. Yeah, indeed. But really interesting in the same. Well, I don't know. Maybe next time you could talk more about non-commutative thing
Yeah,
next time.
I can. But
Yeah.
I'm afraid that there will be less audience.
Well, we actually we don't really care about this about well
Well,
don't care.
we just open the live and talk.
Yeah, yeah, that is that what we do actually.
I see. I see.
Okay. All right.
But
Okay.
Con will be here for sure because he loves this kind of stuff.
Yes, indeed, actually.
Mhm.
Anyway, so I think well, it's about time.
Right.
The end of the activity, and so I would like to thank our speaker, Dr. Apimook, and everyone to stay with us for this. I think about hour, right? Lovely speaking. Yep. And before you go and we go, could you please spend your time on the survey form that
Mhm.
actually put there, and you can see. And yeah, you can put all the comment, anything that you would like to suggest about the talk or the topic that you would like to listen. That, then we can look at your comment and we can improve our activity next time. And so that would be it for this talk. And then see you again for the next if colloquium number 13 next month and in October. All right, stay tuned then. Thank you very much. Bye bye.
Bye bye. Bye.